Hi, everybody, and good morning. Welcome to day 4. And today we'll have lots of state counting and so on and so forth, I suspect. And we're going to open our morning session with Abhiram Kidambi from TUVN, who's going to tell us about modular quarter BPS entropy from half BPS states in 4D and equal to 4. Okay, Abhiram, over to you.
Thanks, sir. Before I start, I just want to thank Gabriel and Suresh for putting together this workshop to facilitate, basically bring us together this pandemic. And I just want to ask, audible at fine? Can you hear me?
Abhiram, no. Try saying something.
You hear me?
Yes, this sounds fine for now. Yeah.
Sounds
the sound
fine.
is a
Okay.
bit scrambled though, so sometimes it's on and off.
How about is it? I mean, my internet does it unstable. Sorry. Let me try this. How is better? Or?
No, I think you're frozen. I think it's your connection. I don't think it's the
seems
sound
like
necessarily.
The connection. Yeah, it's not hardware. It seems just to be slow connection.
Sorry.
Yeah.
It's slow connection.
Yeah. Are you on a Wi-Fi
Perfectly.
or do you have a LAN connection?
I'm on Wi-Fi. I don't know LAN connection.
Yeah, we can. You can try switching off your video. I don't know if you can do screen share with that. Try switching off your video.
I think screen share works.
Yeah.
This is better now.
Slightly better. Okay, let's try to see. Let's see. Let's carry on for a moment.
Okay. So in case I'm not audible, please know I've opened my chat window so that you can. Oops, sorry. I have my chat window open, so in case I'm not audible, please just write over there and I can try to start something else. So let me start. I already wasted a minute. So I would like to thank Suresh for putting together this amazing workshop. Actually, we're in beautiful Lisbon, but I wanted to give a nice Lisbon link, so that's why I've got the Castle Sun in the background. So I would like to talk about some work that I did with Samir and Raza and Abhishek Chaudhary on counting modular quarters entropy from half BPS states and 4D and equal 4 theories. And there also is a slightly joke title to this talk, which is which basically counting all dyons that don't die for last time. So this is based on this paper by Samir, Abhishek, and Tim. I will not be able to go into the full technicality of the entire calculations, especially the number theories that are all from the supergravity side of it. So I do refer you to this paper in case you have more questions, but feel free to chime in with any more content in the talk. Okay. There are quite a few people in this audience who probably have heard this talk or some version of this talk for free. And so I give advice of Fermi, who basically said we're underestimate the joy that people get from hearing something they already know. So with this, I'm going to start a key idea of the talk. The idea here is to cover type 2 compactification K2 or radical compactification C6, which gives us a 4-dimensional n equals 4 theory. Now, this 4-dimensional n equals 4 theory gives us two sort of dyonic black hole solutions, one being half BPS and the other being quarter BPS. I sort of say dyonic half BPS solutions, but later on during the talk, I will probably refer to these half BPS solutions as being purely electric or purely magnetic, but this is something that you're allowed to do anyway. So the key element that distinguishes the half BPS and quarter BPS solutions are that the half BPS solutions tend to have zero area. They do not contribute to the area law term in the Beckstein-Hawking entropy. And the quarter BPS, in fact, they're the only ones that do. The partition function of the half BPS states can be counted perturbatively by considering excitations duals to the half BPS states. And this was done in the 1990s by Hardy-Ramananujan-Rademacher and Jeff Harvey. Whereas the quarter BPS states, they're conjectured to be counted by the inverse of the cusp form. I will define all these quantities later during the rest of the talk. So this is basically just to give you an overview. And the idea is that 1 over phi 10 counts all the quarter BPS states, that is the single center quarter BPS states and bound states of 2 half BPS states, which basically effectively behave as a quarter BPS state. Now, because they're bound states, you have wall crossing effects, and one could try to remove the wall crossing effects from the 1 over phi 10. And in order to count the single center quarter BPS states, one ends up with Mach modular Jacobi forms. And this is something that was studied by Dabholkar, Murthy, and Zagir. I think Samir is in the audience here, I'm not too sure. I think Val also is in the audience. So that's the key idea here. But at the exact same time, we want to figure out a way in which we can compute the degeneracy of these Mach modular Jacobi forms that cover the single center states exactly. And we will basically be doing that by an exact formula and using certain ideas such as black hole metamorphosis and the Rademacher expansion for Mach Jacobi forms, together with the Fourier expansion coefficients of 1 over eta tau to 24, which basically counts half BPS states. So basically we take the 1 over eta tau to 24 plus metamorphosis and Rademacher expansion, and in a nice formalism, we can use that to count the single center quarter BPS states. So that's basically what's going on over here. So I want to give a few key points to just keep in mind for the rest of this talk. The first point being that the BPS black hole partition functions are automorphic forms that can be computed from the superconformal field theory. So as an example, we already mentioned the half BPS states. These are computed by the 1 over eta tau to 24. And the second point is that the black hole degeneracies can be extracted charge-wise from the Fourier coefficients of the automorphic forms. So for example, if you again consider the 1 over eta tau 24, the Cn Fourier coefficients basically capture information about the degeneracy of the black holes. So in this case, they would capture the degeneracy of half BPS states. And the third point is that you only need to know, if you want to compute all the Fourier expansion coefficients, you only need to know a few expansion coefficients, basically the ones that are known as the polar terms, which in this case would correspond to the terms with q to the -1 powers. There's only one of that. And using this polar term, and the fact that these are modular forms or Mach modular forms later on, these properties are enough to basically compute all the Fourier expansion coefficients exactly in some asymptotic limit. So this is another Rademacher expansion. So these are the 3 key points that we will revisit, we will use throughout the rest of the talk. So let me first start with explaining why the black hole entropy for quarter BPS states is in fact Mach modular. So we are going to be considering these dyonic black holes. Let them have an electric charge Q and a magnetic charge P. As we know from the Dijkgraaf-Verlinde conjecture, these are counted by the inverse of the Gusa-Cusp form 1 over phi 10. So the 1 over phi 10 basically has 2 representations. For number theories, there's the Burchard's lift, the multiplicative lift, which is the one that I've written down over here. And there's also an additive lift, which I have not written down over here. So the Burchard's lift over here basically allows us to write down 1 over phi 10 Gusa-Cusp form as this product. And here you have these interesting notations where NML greater than 0 basically means that L is definitely less than 0 if M and N are both 0, or else L can take a range of integers if M and N are greater than or equal to 0. Also, what's important here is the coefficient that appears in the exponent over here, the CK3. The CK3 are basically the Fourier expansion coefficients of the elliptic genus of the K3 surface. And this is not really surprising because this 1 over phi 10 really is a partition function of a symmetric product orbifold that Alejandra mentioned in her talk for K3 surface, K3 sigma models. So you have the elliptic genus of K3, which is a well-known Jacobi form, which is 2 phi 01. And you can do a Fourier expansion of this, and the coefficients that you get out of the Fourier expansion, CNL, are what I will refer to as CK3 of delta, delta here being 4n minus L squared. So this is the same these are the same Fourier coefficients that sort of sit in over here, but delta here will be 4mn minus L square. And the difference is because this is the elliptic of K3 is a Jacobi form of index 1. So the M contribution is just trivial. So as far as we're clear on that so far, I should also make a point that this delta here is related to the charge discriminant, which is basically given in terms of the electric, magnetic, and the P dot Q angular momentum, so-called T-dual invariance. And this discriminant that we have over here is constructed out of T-dual invariance P square Q square and P dot Q, and is in fact a U-dual invariant quantity. Okay, so that is something that we want to keep in mind. Oops. So if you want to extract the degeneracy of the quarter BPS states, one could, of course, try the same philosophy that we had in a few slides ago, which is that you try to do a Fourier expansion of the 1 over phi 10 form. And basically, that would give you this Fourier expansion, which can be related to the degeneracy of the quarter BPS states with some electric charge invariant T-dual invariant N, magnetic charge T-dual invariant M, and the angular momentum T-dual invariant L. And you can use this to compute the degeneracy of the black holes using this integral over here. Now, there is a curiosity that sort of stems from this integral, which is that this is a contour-dependent integral. And the codependency sort of highlights the fact that 1 over phi 10, in fact, over here, is a meromorphic function. That means that it has a double pole at z equals 0 on the Siegel upper half plane, and it's sp2z images. So interesting, sp2z is basically what I would refer to, I mean, what I call sp2z over here is similar, is this exact same thing what Alejandra called sp4, I think, in her talk on symmetric product orbitals while discussing Siegel paramodular forms. Anyway, so we have the 1 over phi 10 over here, which has a meromorphic function. And therefore, when you integrate it over a contour which encompasses a double pole at z equals 0 or any of the other sp2z images, it picks up a residual contribution. And this residual contribution basically means that at these poles, there's a discontinuous jump of the quarter BPS index. And there's a supergravity interpretation for this, which is that you have a bound state of 2 half BPS states, which sort of decay at these walls of marginal stability. And that is the radius of so the radius of the bound state diverges and goes away to infinity. And this was studied in a very well-known paper by Frederick Denef back in the early 2000s. At this point, I just want to ask again if I'm still audible or if there are any problems with the internet.
Yeah, you're fine. You're fine. Go ahead.
Okay, great. Thanks.
Yeah, we can hear you. It's good.
Okay. Also, if there are any questions, please feel free to chime in. There are lots of things which I have not explained entirely pedagogically. So if there's anything unclear, please feel free to ask me. Okay, so if you look at the previous expansion over here, where it's the Fourier expansion of 1 over phi 10, and I gave you information that there's a double pole at z equals 0, you could try to repackage the entire Fourier expansion into something known as the Fourier Jacobi expansion. Now, this is not really a correct mathematical statement, but for the idea of physical intuition, it sort of works, which is that you sort of retain the pole structure in a Jacobi form over here, which is psi m tau z. And this is the Fourier Jacobi expansion of 1 over phi 10. And all these psi m's over here, these are Jacobi forms of weight minus 10 and index m. And because in the previous slide I showed you that the double pole is at z equals 0, this psi m still is a meromorphic function. Okay, so these guys are the ones which are now responsible for wall crossing, right? So if you want to compute the single center quarter BPS black hole degeneracies, what you want to do is remove the residual contribution to the integral. Okay, and this was done in a very well-known paper by Dabokar, Murthy, and Sagir. And the way you do it is that you first start off by averaging over the residues at all the double poles, and that is given by the averaging function over here. And using this averaging function, one can actually define something known as an Appel-Lurch sum. So this definition, I mean, this derivation is something I just cannot do during this talk, but I refer you to the paper of Dabokar, Murthy, and Sagir for more details of this derivation. This Appel-Lurch sum basically is the one that is actually responsible for the wall crossing effects. What I mean by this is that if I try to expand this Apple sum in different strips on the upper half plane now, I would expect, I actually see that it has different Fourier coefficients for different strips or different regions in the upper half plane, right? So Apple sum really controls the wall crossing that we have over here. So you can use the Apple sum and basically put it together with other contributions from the Dedekind eta function, which is P24 of m plus 1, which basically is the q to the mth coefficient in the Fourier expansion of 1 over eta tau to 24, divided by the eta tau 24 itself, times Apple sum over here. And this basically is the polar piece psi m p of tau tau z. And this also has a nice supergravity interpretation, that is that it removes the center of mass motion, make a monopole, and therefore removes all these unnecessary wall crossing effects. So this also has a supergravity interpretation. So together, all of these, once you have this psi p of tau comma z, you can use the psi p to basically construct what is known as psi mf. So that is that you have these Jacobi forms, which are defined for each value of magnetic charge. And from this value of the Jacobi form for a given magnetic charge m, you do this entire procedure, compute the absolute sum for magnetic charge m, compute the polar piece for some magnetic charge m, and then you can basically define the psi m finite piece for magnetic charge m. Now the idea here is that you've removed the wall crossing effects coming from this absolute sum over here. So you would expect that this psi mf of tau comma z captures the single center quadrant BPS degeneracies. So this is the entire work of the Hokumoto here. There is, of course, a sort of trade-off over here, which is that by subtracting this psi m p from psi m, you reduce, or you're now restricting yourself to a function that is holomorphic, but it is not necessarily modular. It's a Mach modular Jacobi form. And of course, you can make this modular again, but by adding something on the shadow, and you have to choose the shadow in such a way that it has the correct growth properties. All of this is explained in the paper by Hokumoto and Zagir. And of course, but when you do this, you recover back the original function, and which again is a meromorphic. So there's a sort of trade-off between meromorphicity and modularity over here. The psi MFs are also, they're Mach modular, but they're still periodic functions in tau and z, which therefore allows us to do a Fourier expansion in tau and z. And therefore, using the Fourier expansion, you can compute this CMF and L, which are the Fourier expansion coefficients, and these are the ones which actually capture the degeneracies of the single center quadrant BPS black holes for us. Okay. But of course, we want these guys to be weakly holomorphic, which means that there are a finite number of terms with charge discriminant delta equals 4mn minus L squared, which are less than 0. So you actually expect these sort of terms to exist because firstly, the psi MF is counting single center quadrant BPS black hole degeneracies, which are, of course, they're black hole solutions, so they have a particular growth of degeneracies with charge. This is the Cardi growth, basically. So you expect that for Cardi growth to be there, you expect these terms of the kind delta equals 4mn minus L squared to exist in your entire, to exist in psi MF. Okay, we will also call these polar terms as negative discriminant states for very obvious reasons, that the discriminant is negative. So these delta less than 0 states, they sort of seed the large black hole entropy. The first way is obvious, which I just said, is that they're the ones which are responsible for the Cardi type growth, the Ramanujan growth of Fourier expansion coefficients in psi MF. But secondly, and most importantly, these are the terms that are required in order for you to do the Hardy-Ramananujan-Rademacher circle method, which means, I'll tell you what this means in the next slide. But the idea is that you have these delta less than 0 states, you take the coefficients of delta less than 0 states, and then you can use that along with, in our case, Mach modularity to compute all the other coefficients, Fourier expansion coefficients in psi MF. Okay. So that is the Hardy-Ramananujan-Rademacher circle method. So this particular example over here, that's the one that was, I think, derived in a paper by Francesca Ferrari and Valentin Reis. And of course, this is also found in the paper that I mentioned at the first or second slide of this talk. So here the idea is that you take as input the terms which have coefficients with, you take the coefficients of terms with negative discriminant, and you plug that into this giant machinery over here, which is the Hardy-Ramananujan-Rademacher circle method, or the Rademacher expansion, as I would call it. You plug that inside over here, and then basically you recover the Fourier expansion coefficients of some other positive discriminant state or something. So here, of course, this is a very laborious formula to look at, but I won't go into the full details of this formula over here, but the key ingredients are firstly what is known as the Kloosterman sum. So the Kloosterman sum basically is given in this form over here, with psi is some sort of a multiplier system and gamma is some SL2Z matrix. Then you have the I Bessel functions of some weight. And these Bessel functions are interestingly very important for us to guarantee the asymptotic growth. And this is something that you also get from the localization aspect in supergravity. And for the localization in supergravity, I actually refer you to a paper by Valentin Reis and Samir Murthy from 2016. And finally, you have these functions down over here. I mean, it's a complicated mathematical formula, but we don't have to work with it at this very instant. So the key point that we want to remember here is that you plug in these negative discriminant state coefficients over here into this giant machinery, and you recover some positive discriminant coefficient over here, meaning that you can compute the single center black hole degeneracies from the negative discriminant states alone.
Can I ask a question?
Yeah.
It's Boris speaking. Can you elaborate on the physical meaning of these polar states in psi f? Since this psi f was supposed to count single-centered black holes, but there are no single-centered negative discriminant.
Very good. That is with the rest of this entire talk. So I will come to this question in maybe about 3 slides or something.
Okay, sorry.
Okay. So of course, like now we would think that this is the end of the problem, and you basically have information about these negative discriminant states over here, and then everything works out fine. But the sort of motivation to study this in a bit more detail came from the aforementioned paper by Samir and Val in 2016. And the idea here was, I think their motivation was to study this from the point of view of exact holography as well, which is that if you try to compute the degeneracy of quarter BPS states in n=4 supergravity from the localization of n=4 supergravity, from the exact holography dictionary, you would expect that these match and perfectly head on with the microscopic degeneracies that you would compute from psi-MF. However, the problem that they had noticed was that, at least of the leading order, there were certain negative discriminant states which did not match. That is, that computation of the degenerate negative discriminant states did not go through exactly for certain values. Now, that of course is a bit problematic in the entire case, because we know that the negative discriminant states are the ones that see the black hole entropy. So if there is a slight discrepancy between the cases, between the computation of negative discriminant states from the supergravity side and the microscopic side, then it of course throws the entire problem wide open, because A, the negative discriminant states are responsible for the Hardy-Ramanujan growth, and B, they see the entire black hole entropy. So this kind of is just a one-slide motivation as to why we decided to study these negative discriminant states a bit more detail. I actually want to come to Boris's question, the next slide, I think. Okay, I'll come to the next slide. So here I'm going to make a few statements which would have actually been better off motivated if I had spoken about the supergravity side of it as well. But let's go back to the idea that 1/510 is a contour-dependent integral. The degeneracies that you extract from 1/510 are dependent on the contour of integration. Now we know from the attractor mechanism basically meaning that only the near horizon black hole charges fix all the degeneracies, and the asymptotic variation, the moduli, don't really matter that much. So you can choose the attractor mechanism to study this from the supergravity side. And as it turns out that you can choose a contour in the Siegel upper half plane that corresponds to choosing the attractor values from the supergravity side. And this is, of course, detailed out in the paper that we have over here. And this is precisely the one I think was studied by Cheng and Verlinde in their paper as well. And we also know that the Fourier Jacobi expansion reduces the Siegel upper half plane to just the upper half plane. And the statement that the upper Lurch sum is basically the one that's responsible for wall crossing in the upper half plane because it has different Fourier expansions in different regions or different strips of the upper half plane. So once you put all this together, it tells you that you can break down the upper half plane into different chambers, which are in some sort of an axial dilaton type moduli space. And there is a chamber in this axion dilaton type moduli space that corresponds to precisely choosing this attractor contour. So it looks something like this. And this chamber R is the one that corresponds for us. I think I might have had the wrong figure over here because I should probably mention that this is the region R is bounded by the walls by these green lines, which go from 0 to I infinity, 1 to I infinity, and then 0 to 1. So that's a semicircular wall 0 to 1, and then two walls that go from 0 to I infinity and 1 to I infinity over here. I think I got the wrong picture, apologies. So this chamber R is the one that we are actually going to be interested in. And for this chamber R, the generic statement that we would like to make here is that all the positive discriminant states are single center quarter BPS states. Now, subtraction of the psi MP term removes the bound states that sort of removes the bound states that appear from these vertical walls over here, the green walls, and the negative discriminant states that seed the black hole entropy, a single center black hole entropy, they appear from the semicircular walls over here. I'll show a better picture in maybe a slide or two. But now we come to the question that Boris asked, what exactly are these delta less than 0 states? So the physical interpretation, which was first given by Ashok Sen and then utilized in our paper, was that these delta less than 0 states in psi MF are sort of residual bound states of half BPS states. You can call them monopoles or instantons. They're not necessarily black holes for the reason that a black hole, the entropy scale says square root of delta, e to the square root of delta. And if you have a negative discriminant, that doesn't really make much sense. So you can't really call them as honest to God black holes. But there are some half BPS bound states that still linger. And these are what are negative discriminant states for us. Okay, so basically the problem of obtaining the single center black hole degeneracies in this region R basically reduces to a problem of counting precisely all the negative discriminant states in region R, because then we use the Rademacher expansion and then compute the single center black hole degeneracies. Okay, so let's now go into a bit more, let's switch gears a bit. So now our key aim is to count single center black hole degeneracies. So how am I doing on time? I've got about half an hour left. So the key aim here is to count the single center black hole degeneracies, the negative discriminant state degeneracies in the region R. So we can start looking at the walls that describe the region R we can divide them into two categories over here. The first one are these T walls that start from an integer. For example, over here, these are all integers where the green walls start off, and they go all the way to I infinity. We will call these guys as T walls. And then you have semicircular walls, which end and start on rational numbers on RE of tau. And the key point that we want to remember here is that for each of these walls over here, there's an associated matrix that belongs to PSO2Z. So basically, if you have an endpoint if any points which go, that's a wall that goes from Q over S all the way to P over R over here, that means this wall is described by a PSO2Z matrix of the form PQRS. Okay, there are of course these matrices also for the T walls, but it's just that one of them goes to 0 over here. I think the R value goes to 0, and that would describe the ones that go for the I infinity walls. Okay, So we have these SLC matrices, and therefore the set of all walls in the upper half plane can be characterized by this set over here. That is, we now reduce this to three basic sets. The first one is the so-called gamma S plus, where you have a matrix PQRS in PSL2Z such that R and S are greater than 0. You have one in gamma S minus, which basically is PQRS. R is greater than 0, but S is less than 0. And basically, these would correspond to wall. Gamma S plus would correspond to walls that go all the way from 0, 1, 2, I mean, this side of the region R, whereas the gamma S minus would correspond to walls that are on the other side, to the left of the region R, basically semicircular walls. And then finally, you have the walls that correspond to the T walls, which are basically gamma PQRS, such that R and S, R times S equals 0. So you can sort of see that gamma S plus union gamma S minus union gamma T basically is just a set PSL2Z over here, right? So each of these walls could in principle seed black hole the negative discriminant states in the region R. And oops. So basically you want to keep track of which walls would indeed contribute. But let's also first figure out how the negative discriminant states contribute to the region R. Okay, so we know that psi MP removes the contribution from the T walls because these are the apple strips. So you take them all at one fell swoop. So the logical conclusion here is that the delta less than 0 bound states, they could come only from S walls, which meaning the semicircular ones. So let us consider a state delta less than 0 with NML being the T-dual invariance. Now, at a wall PQRS, there's associated breakdown of this one particular kind, so the electric and magnetic charges split into this particular way over here. We will call this one center, one of these half BPS states in this breakdown as an electric center, and the other half BPS state that comes from here is the magnetic center. And so you take this guy, SQ minus QP would be the electric charge of the breakdown, and minus RQ plus PP would be the magnetic charge of the breakdown, so to say. And for the associated breakdown, of course, you have the so-called other T-dual invariants, N gamma, L gamma, and M gamma at the wall gamma. And they are given by this expression over here. So it's basically just putting down SQ, QP, and then multiplying them all together. So the obvious thing that we have here is that the discriminant of N gamma, L gamma, and M gamma is almost the same as the discriminant of N, M, and L because the delta is a U-dual quantity. Right. So that is how a charge vector breaks down at a wall of marginal stability. Right. So let us move on to the next part, which is to figure out if and when a bound state would contribute to the region R. So what we have here is that we have a region R, which is basically bounded by these semicircular walls and these vertical walls over here. So when would there in principle be a delta less than 0 state seeding the single center entropy in R? Okay, and for that you need to ask the question as to where the bound state exists with respect to the wall that you're considering. So for example, let this region R be somewhere up over here, and let's consider a semicircular wall that goes from Q or S to P or R. Now, the key idea is that if the breakdown has an angular momentum L gamma associated to it, now if you have an orientation, let the orientation of the wall go from Q or S to P or R. Okay, so it's something like this. Now, the key idea is that if L gamma is less than 0, then it means that the bound state exists to the right of the wall with respect to the orientation. And if L gamma is greater than 0, then that means that the bound state exists to the left of the wall with respect to orientation. So naturally, if it exists over here, it can seed the single center black hole entropy. And basically, that's what we want to look for over here. Okay. And thirdly, we can also define a different function. So you can use this quantity along with the orientation to figure out if and whether a particular decay would contribute to the region R. And to do that, you define a new theta function. So this is a sort of bookkeeping step function that is sort of required, but in the end actually plays a huge role in computing the degeneracies exactly. So this theta function that we define over here is defined with respect to the region R and for a wall gamma. So basically it's the sum over, it's the sine of L gamma, whether it's positive or negative, plus this function O gamma of R. This O gamma of R basically tells you what the orientation of the walls actually are. So it's +1 if the gamma is in the set gamma S plus. That is if it lies in and to the right of the region R, all the semicircular walls, and it's -1 if the walls lie to the left of this region R here. So that's just telling you about the orientation. So take the orientation of the wall, which can be plus or -1, plus the sine of the L gamma at that particular wall. That you can use to define this theta function over here. Now you can plug that into a very rudimentary formula. So I should point out that the first rudimentary formula to consider these sort of negative discriminant states was studied by Ashok Sen in his 2011 paper on negative discriminant states. But now we are going to refine this. So we have in principle all possible walls which could contribute negative discriminant states into the region R. So as a bookkeeping device, you basically insert this theta function into that particular contribution formula, and you sum over all possible walls in gamma S, right? So this seems like a nice formula because it tells you that this is an honest to God formula, because if you sum over all the infinite number of walls, then you're bound to get the correct answer. But of course, computationally, this is not a very nice formula because it's a sum over an infinite set. So what we want to try to do is try to constrain it at this point. So we want to restrict the elements gamma that contribute to the sum over here. Okay. So there are 3 cases of negative discriminant states that we will be considering. So I have about, I think I've got about 20 minutes time-ish, but a little over 20 minutes. And I probably realize now that I should have put a bit more detail in over here instead of just stating the results, because I expected to have much less time than I have right now. But so I will finish a bit earlier than expected. But let me try to just finish with the negative discriminant state picture. So the first case, the negative discriminant states that we have are when you have the n gamma at a particular breakdown greater than or equal to 0, and m gamma of a particular breakdown also greater than or equal to 0, the total discriminant being negative. So you can use that to solve for bounds on what possible values of gamma will contribute. And the way you do that, of course, is you have 2 inequalities, one equality from this particular set of equations here, plus the restriction that you want to restrict only to those guys which contribute into the region R. So you can use these 3 or 4 constraints, 3 constraints and 1 equality, and to solve for bounds in gamma. So what we in fact find is that you only get contribution to this sum over here only from those sets, only from those walls gamma, which are associated SL2Z matrix PQRS, such that PQR, oh, this should be an S, sorry, PQR and S are in fact bounded by M, right? So this really drastically reduces the size of the contributing walls to this region. So it tells you that of all the infinite number of walls that could in principle contribute or seed the negative discriminant states in region R, only a finite number of them would contribute for the case that n gamma greater than 0 and n gamma greater than 0. Okay. There is, of course, a subtlety that sort of comes in now when you hit the value, the critical value or the lowest possible value of n gamma and or m gamma. So let's consider the case where, first consider the case where n gamma or m gamma equals -1. So this would correspond to either an electric bound state metamorphosis, as we will call it, or a magnetic bound state metamorphosis. Okay, so what exactly is a bound state metamorphosis? So let's take a wall gamma for which you have n gamma equals -1 with m gamma greater than 0. All right. So for this wall, you can define another wall, which you call its metamorphic dual for the time being, given by this expression over here. And the idea is that gamma and gamma tilde both have the exact same contribution to the polar coefficients, C tilde, M, and L. They both contribute or see the exact same number of negative discriminant states. Okay. Similarly, for the case of M gamma equals -1, that is a magnetic metamorphosis, and N gamma greater than or equals 0, you can also define a dual metamorphic dual wall for which, again, gamma and gamma tilde see the exact same number of negative discriminant states. Okay. The philosophy of bound-state metamorphosis is that a wall gamma at which bound-state metamorphosis occurs contributes the exact same degeneracy of delta less than 0 states in R. And there's a key principle is that a wall gamma would contribute to the region R if and only if gamma tilde also contributes to the region R. And if they both contribute to the region R, you need to identify both their contributions at once. I actually put in a reference by Ashok Sen over here, but I think it got deleted. So I apologize for that again, but this actually was first studied by Ashok Sen in his paper on negative discriminant states in 2011, right? So bound-state metamorphosis for us basically tells you that if you hit N gamma or M gamma equals -1 for us, then you in principle have to identify different sorts of contributions coming from different walls, subject to the condition that all the walls do indeed contribute to the region R. So how does that look like precisely? So this is for the case where, for example, M gamma equals -1, but the case of N gamma equals -1 also follows analogously. So let's take, for example, a particular wall. Let's start out with this guy in the non-contributing case over here. So what we see here is that you have the original wall gamma, for which you have, let's take L gamma is going to be less than 0. So obviously this negative discriminant state contributes downwards. It does not really reach the region R. But you also have a dual wall gamma tilde, for which you sort of sit inside and contribute to the region, which does see the negative discriminant state in the region R. So if we didn't usually use the principle of negative discriminants or bound-state metamorphosis, then what would have happened was that we would have ignored the contribution from this wall, but then we would have taken into account the contribution from this wall. And of course, that would have given us the wrong answer. But instead, what we need to do is that because we see that this wall does not contribute while its dual contributes, we throw away this guy entirely. Okay. And similarly, for this case over here, we have the original wall gamma, which does contribute negative discriminant states into the region R, but we have its dual wall gamma tilde, which does not contribute its negative discriminant states into the region R. So basically, you sort of throw this contribution away. And similarly, you have different sorts of cases where neither of them contribute or only one of them again contributes. But you only expect to see one contributing case. So in principle, what you expect to see is that, or if we were being naive about this entire approach, would have been that we would have 1, 2, 3, 4 contributing cases. And of course, you would have overcounted the number of negative discriminant states. But bound-state metamorphosis sort of throws away all these contributions. And the only honest to God contribution that remains is when you have the original wall that contributes into the region R, and its metamorphic dual, gamma tilde, also contributes to the region R, in which case you count both these negative discriminant states as only one. Okay, so that's the principle of bound-state metamorphosis. This is kind of interesting because firstly, it tells you that there's sort of a nice Z2 orbit action for L gamma and for gamma and gamma tilde, which I think we will come to at a later point in time. But most importantly, what we want to consider is the case when both M gamma and N gamma equals -1. But before we do that, let's actually see what the contributing matrices would actually be for this case. So we have, again, now different equalities. You have one equality where you say N gamma equals -1 or N gamma equals -1. Using this principle from bound-state metamorphosis over here, you can translate that into mathematical constraints, which would give us bounds on the contributing set of gamma in the total sum of negative discriminant states in the region R. So once you do this, what you realize is that the contribution, and you work out a lot of algebra, you realize that you only get contribution from those walls in the set of semicircular walls. such that, again, it should be an S. I think I made a mistake in the entire LaTeX formula, sorry. You see that the only contribution from gamma and gamma S is such that PQRS are all bounded from above strictly by the absolute value of n plus 1. Okay, so that is, again, restricts the whole nature over here. So that would be the case which actually goes for both electric Boundary metamorphosis and the case of magnetic boundary metamorphosis. And in fact, the analysis for both these guys are actually very similar to each other because of the nature of electric magnetic duality. So it's just really an S-dual transformation of the entire analysis, which would give you the exact same answer for the case of the magnetic case or also for the electric case again. The tricky case, of course, comes from when we have the case when both n and m gamma being equal to -1. That is, they're both the lowest possible values that you can take in the Fourier expansion of 1 over eta to 24. So this is a bit more tricky because here, in this case, you can have an infinite set of identifications that can go about. In fact, you have two different set of infinite identifications. So let's consider a wall gamma at which both m gamma equals -1 and n gamma equals -1. So here you can start defining the magnetic duals, the metamorphic duals. I should also state that when you actually consider these magnetic duals, what actually you're doing here is that you're identifying different, so to say, centers. So basically both gamma and gamma tilde, they do contribute the exact same to the degeneracy in the region R, or they basically have the same degeneracy of bound state breakdowns, but also it's important to keep in mind that both n and m at both these walls, gamma and gamma tilde, are in fact exactly the same. So that is, you're just identifying all the walls with the same contribution n and m, with only a difference in the sign of L. Okay, so let gamma be a wall at which m gamma equals -1 and n gamma equals -1. So you can start to define the metamorphic duals for the cases for these guys, and you have an infinite number of these walls that you can actually construct when both of them are equal to -1, and that's given by this sequence over here. Okay, and given a negative discriminant state with n-m-l, and you have a wall gamma at which m gamma and n gamma equals -1, then the idea is that all the gamma I have the same contribution to the polar coefficients of negative discriminant states in the region R, if they contribute to the region R, that is. And the contribution to the region R becomes apparent when we realize that a similar analogy from the previous cases go through, which is that a wall gamma would contribute to the degeneracy of states in R if and only if all its metamorphic duals gamma I also contribute to the degeneracy in the region R. Okay, and as again, you have to identify all the contributions and they have to be counted only once. So for us, this would look like this. So you have, in principle, I should point out they have green dots inside over here. So it might not, I've only drawn 3 walls, but there are infinite number of walls with stretch on either side, and also here stretch inside. So you can basically have 2 different sorts of cases over here. So you have an original wall gamma for which the breakdown has m gamma equals n gamma equals -1, but then you can start identifying an infinite number of walls. And the other case where an infinite number of walls will in fact contribute to degeneracy in the region R. And of course, you cannot count all these walls individually, because then the degeneracy of negative discriminant states would be infinite, which makes no sense. So you have to identify all the contributions of negative discriminant states coming from all these walls over here. And similarly, from the previous cases, we see that since one of these walls does not contribute, but again, an infinite number of walls would in principle contribute, by virtue of the fact that only one of them does not contribute, this entire sort of setup can be thrown out. So using these sort of different principles, you can again basically restrict and try to find bounds on the contributing walls. And again, I think I made a LaTeX mistake. There should be an S over here. And once you find the bounds on the possible contributing walls for the case of dyonic metamorphosis, you actually realize that the number of walls that contribute are all, the walls that in principle can contribute with dyonic metamorphosis are all bounded from this region, are bounded with the case that P, Q, R, and S are all less than equal to n plus 1 in absolute value. However, there is a sort of subtlety over here. I mean, there are infinite number of walls over here. So what does it mean to have walls that are bounded in this region? So basically, it means that there's always one, element of this entire sequence that I defined over here in this set PQRS in this particular bound over here. So that's basically what I mean by it has contributions only from this set. And since they're all identified, you only need to consider it once. Okay. And I should also point out that there is some very interesting sort of number theoretic ideology or a number theoretic structure to this from the idea of Pell equations and everything. Unfortunately, I don't think I have the time to discuss all of this right now. So I would really refer you to our paper, which I showed in the beginning of this talk. Okay, so finally, let's come to the sort of orbit structure and towards an exact formula for metamorphosis. So what we've seen here is that you had three different cases for negative discriminant states to contribute. One is the case for which you only have single walls that contribute to negative discriminant states, and that happens when you have n gamma greater than 0 or m gamma greater than 0. Then you have a particular case of n gamma equal to 0 or m gamma equals -1 or m gamma equals -1, in which case you do have contributions from two walls which sort of need to be identified as one. Okay, so that sort of is like an orbit of length 2, if you could interpret it that way, with some sort of Z2 identification. And finally, there is the dyonic metamorphosis case where an infinite number of walls contribute. So that's like an orbit of infinite length with some sort of Z identification, with the idea that there's one representative in that orbit, which sits in this nicely bounded set of contributing matrices, which would give us the correct answer, or which should seed the negative discriminant states in the region R. Okay, so you can kind of split this into three orbits. So you have this whole identification of metamorphosis that you want to sort of mod out from PSL2Z, but you also know that you don't really have to work with PSL2Z because you have restricted the contribution to only come from certain matrices. And this set of matrices, again, bounded such that P, Q, R, and S are all bounded by absolute values of m+1. Okay, so that really is a finite set that you reduce. You start out with the PSL2Z and you restrict to this particular set over here, and then you can still work on the bound-state metamorphosis. Okay, so with the notion of all these orbits, you can also define a particular a new sort of theta function. So recall I said that all the walls contribute from a particular orbit of metamorphic duals, if and only if all of them contribute. And basically that would mean for us that you could just simply multiply all the theta functions. The theta function either 0 or -1. And if they all do contribute, then they all have to be 1, which would mean that the product of all the theta functions has to be 1, right? And if one of these guys in this orbit does not contribute, then it leads to 0 to this product, and therefore the whole product vanishes. And you could sort of refine this and try to rewrite the entire formula as some finite set, which basically has one representative from the entire orbits of metamorphosis that contribute to the region R. And it's a heavily bounded set that only depends on the magnetic charge +1. Okay, so that's kind of interesting because you've really taken an infinite set of walls and put together this bound-state metamorphosis and put together the constraints that you get on the size of the contributing sets. And then you say there's actually a very small subset of walls, and the subset of walls actually depends on the value of the magnetic charge that you're considering over here. Okay, so of course, the next step is to see if and whether this agrees with the calculations from the supergravity side. And well, there's not really much of a spoiler. Yes, it does agree with the sort of discrepancies that were noticed by Samir and Val. I mean, otherwise, there's no point in writing a paper about it. But let's first try and see if the formula actually sort of checks out along with the principle of bound-state metamorphosis. So you can take one bound state, for example. Let's take any of these ones. So for example, 2, -1, and 2 over here, which has discriminant of -12. And you see that they actually have a different number of walls that contribute, and you have a different set of walls which have -1 and -1 for the electric and magnetic breakdowns of this particular wall. And there are an infinite number of contributions or infinite number of walls that could in principle contribute to the region, to the negative discriminant degeneracies in the region R. However, because of bound state metamorphosis, we sort of identify all the contributions, and you only get out a finite sensible contribution to the net index over here. And similarly, you can also work backwards. So you can look at, let's take, for example, this 201 case. You have different negative discriminant states that contribute. So you have one breakdown that comes from a particular wall with this particular charge breakdown, which gives you 7776, and then another one which gives you 576, and then you have a magnetic metamorphosis that shows up from these two walls over here that gives you value 24, and together that gives you the correct answer, A376. So if you hadn't really taken the correct formula into account or the metamorphosis into account, then what would have happened was that you would have seen this as 8400. You would have counted 24 extra states in this particular degeneracy over here. So this is the kind of check that firstly, it reproduces the correct required number of negative discriminant states in the region R. And then when you put all this together, you see an agreement with the supergravity localization. So it really is sort of the last piece of the puzzle that you need to really nail down exact holography for n equals 4 right on its head. Okay, so I stated before that I might have had a lot more time, and I think that is not really true because I'm almost out of time. So let me conclude at this point. It's really important to study the negative discriminant states in psi-MF, and because of the fact that they are the ones that are responsible for generating the Cardi type growth in psi-MF, and at the exact same time, they're the ones which are required to seed the Rademacher expansion in order for you to be able to compute the other Fourier expansion coefficients exactly in some asymptotic limit. The interpretation that you can afford here to these delta less than 0 states are that these are half BPS bound states that sort of linger, that sort of seed the black hole entropy from the semicircular walls. And the reason they seed only from semicircular walls is because you already removed the contribution from the alert strips, meaning you remove the contribution from the walls that are sort of vertical. And for the very virtue of that, they seed the black hole entropy, they need to be counted precisely. So what we have done here is that we've considered an appropriate chamber in which to compute the negative discriminant states. This would sort of correspond to from the side of using an attractor contour in the supergravity description. And we sort of presented an exact, we definitely presented an exact formula which counts the delta less than 0 states in an appropriate way. The appropriate way meaning that we have taken into account subtleties from metamorphosis. And we have constrained the set of contributing walls heavily. And we've introduced this new interesting theta function, which basically keeps track of whether or not a bound state would be able to seed would contribute to the negative discriminant state degeneracy in the region R. There's therefore this subtlety of metamorphosis, which went largely under the radar, meaning that you need to identify different contributions at certain critical values of electric and or magnetic charges. And once you put all this together, you really get a nice set of a nice formula which computes the number of negative discriminant states inside the region R. There is, of course, a nice implication here, which is that the whole set of matrices that are computed by the whole set of matrices are controlled by the magnetic charge M, because there's just bound on M+1 on each of the entries of the matrix SL2Z, which describe the walls of minor stability that seed the negative discriminant states. And the implication here would interestingly be that the black hole entropy is controlled by a finite number of worldsheet instantons, although I do not know what to do with this information. But it's just sort of an interesting observation, which is sort of interesting and good to mention it. There are, of course, certain computational advantages of these things as well. So which is that you can start with the formula that we present over here, compute the negative discriminant states, use the negative discriminant states, feed it into Rademacher expansion to compute psi-MF. And of course, you can also use the psi-MP for coefficients and put together everything together, and therefore compute all the coefficients of not just psi-MF, but also if you want even the Igusa cusp form. And in fact, this is actually computationally much faster. And the reason it's much faster is that it does not require the laborious decomposition of a Jacobi form or a single modular form into its Fourier expansion coefficients, but rather you start with the Fourier expansion coefficients of a very simple function, relatively simple function, being the inverse of Dedekind eta to the 24, which is obviously a much, it's a function in only one variable, and therefore you compute its Fourier expansion coefficient much easier. And therefore, this sort of renders a computational advantage to computing the entire set of degeneracies of single center quarter BPS black holes. And even if you want, you could even take it one step further and say this the same for 1 over 510. We actually have a statement or two on how computationally advantageous it is in our paper as well, but it's much faster. And finally, this is the most important conclusion that I would like to say. This is relating to this OSV type argument. I didn't really describe much over here because it would sort of require me to write down the tree level and the third one loop correction to the pre-potential from the supergravity side. And since I did not mention it, I decided not to mention the formula. But if you look at the paper that we have, and also the paper by Samir and Val, mostly it's the paper Samir and Val, the one loop correction to the pre-potential, for the n equals 4 case, it's a one loop exact correction, and that is the log of the Dedekind eta to 24 in terms of x0 and x1 from the complex geometry side. And these are precisely the terms which we expect to see in our formula, and we do see in our formula in terms of the coefficients of the two Fourier coefficients of the Dedekind eta that sit over here, the dmn, dnl. So basically the whole idea is that you can sort of seed or compute a single center black hole entropy, which is a non-perturbative quantity, in terms of purely perturbative quantities, in terms of Dedekind eta function, which are actually half BPS states. So you can take this half BPS degeneracy plus the Rademacher expansion in order to get the quarter BPS state. And this is a very nice it's not really an OSV type argument, but it's sort of an OSV argument with extra steps meaning Rademacher here, which is that you really need to know only the perturbative corrections or the perturbative terms in your theory and use that to compute the non-perturbative black hole entropy. And of course, in our case, it's perturbative because of the de Broglie-Hardy states. And this is, of course, a very interesting comment that probably should be made at this point. And I want to start with outlook over here. There, of course, is the gravitational interpretation of negative discriminant states, which are still sort of unclear at this point. There was, I think, an attempt by Suresh, Atish, Davolkar, and David Gayato back in, I think, 2010 or 11 at some point. And Atish actually asked me to look a bit more into this, but I think the pandemic sort of sidetracked me from this project. And I think this is something that I would like to look back at some point in the future, near future. And of course, then there's also the CHL extension to the entire formula to ask you whether this holds not only for phi 10, but also for phi k when you've done a CHL orbifold. And I believe this was done by Gabriel Cardoso, Suresh, and Matteo Cello quite recently. And if I'm not wrong, this might probably also be the title of the next talk. So with that, I will stop and introduce more Portugal pictures. Thank you.
Okay, thanks, Abraham. The lovely titles. Thanks, speaker. Questions? Comments?
Yes, Boris speaking. I had a question.
Yeah.
I got lost a little bit in the details of black hole metamorphosis, but there was one nice formula which seemed to encapsulate it nicely. I think that's the last one that you showed in that formula here, where you have a sum over some kind of coset PSL2Z mod BSM. What is this? Maybe you described it in your talk, but what is BSM? Is it a subgroup of PSL2Z? And can you?
So this BSM. Okay, so this is. It's not a subgroup for sure. It is a subset, and it's basically just a set of all these walls that lie in these different orbits of contributing of these identified walls. So, for example, here for the case of, let's take only the m equals -1 or n gamma equals -1 case, then
I actually lost track what n gamma and n gamma was at
so
an early
n gamma, so you start off with a charge vector MNL or NML, and which has negative discriminant. And this charge vector would basically have, because it's a negative discriminant state, the interpretation is that these are bound states of half BPS states, and therefore there's a decay at different volts of marginal stability. And when you decay at a wall of marginal stability, there are new electric and magnetic charge vectors, there's new electric and magnetic charges. And at a wall gamma, that electric and magnetic charge is what I call n gamma and n gamma. Okay, so it's basically this expression over here. So at the wall gamma, you basically have the breakdown of PQ.
Okay, now I see the definitions. Yes, thank you.
So there, this guy would be n gamma, this SQ minus QP, that when you square that together, that would be. So basically, the idea is that you take all these set of
Yes, what I was asking is whether there is a concise definition of what you call gamma BSM. It looks like you have to go through the details of this.
I think you have to go through the details. It is definitely not a group structure. So as far as I computed, I don't think there is any precise or beautiful mathematical structure to it. So it's really just doing the dirty work and trying to define this as a set of walls, which you have to remove due to the nature of identification due to bound state metamorphosis.
Sorry, can I make a comment, please?
Yeah.
In fact, I was going to make this comment anyway, but this is, I think, a good time to do it. So there's something which we worked out in our paper, actually, you did, which is very beautiful, which has to do with this beautiful mathematics, which has to do with the structure of the BSM. And perhaps it's worth mentioning. So they're actually, maybe you want to do it. I mean, let me just say a few sentences, but maybe you should do it. Is the fact that there are sort of these three types of metamorphosis, and two of them, electric and magnetic, are just finite. They're just finite sets, so you can just write them down completely explicitly. It's the third one, the dyonic one, which has actually an infinite set of identifications you have to make. And there, the question is there some structure? And it turns out that there's a very beautiful structure that those infinite set of identifications fall into orbits of some basic elements, and those orbits are actually just the solution sets of the Brahmagupta-Pell equation. This is well studied. It's just the order units of you're studying some real quadratic field or imaginary quadratic field, depending on the detail, and it's just the units of that field. So there is some very nice structure that we worked out.
Yeah, this is something I didn't want to touch upon here because I didn't get into the entire structure of the Pell equation. But yes, like Samir said, there is this very interesting set of orbits that you can generate. It really boils down to understanding how, for the case where you have this dyonic metamorphosis, so the case where you have only one single center metamorphosis, electric or magnetic, that's trivial. You have two walls, just some Z2 identification, like Samir said. But the case where this m gamma equals -1, that is a dyonic metamorphosis, they have this infinite set of walls that contribute. And you want to ask, if you try and look at the constraints on how the m gamma, on what kind of walls would in fact contribute, it really just basically looks down into solving quadratic equations with particular set of constraints. Most of them are solving for integrality constraints. And the nature of the quadratic form is such that you want to look for solutions which look a lot like these generalized Pell equations. So from these generalized Pell equations, like Samir just said, you can start generating an infinite class of orbits. That's the way the Pell equations actually work, right? So you take one solution, and then from that one solution, you can generate an infinite number of solutions. Similarly, you can find different sorts of class of solutions over here. So there really, for the case of the dyonic metamorphosis, there really is something much nicer. But this something actually, one can sort of appreciate quite easily too. So if you just look at the paper our paper over here that I mentioned, around the case where m gamma equals -1, there is one particular case where, if I'm not wrong, let me try to recollect which part it is. So you're really trying to ask what are the conditions under which a particular wall gamma would contribute. The wall gamma would therefore basically be, when I say a wall gamma, what are the constraints on PQ and RS such that m gamma equals -1 would be a legitimate solution such that PQRS is an element of PS not to Z. Once you plug this requirement in, integrality constraints reduce you to this Pell equation type structure. So you do get like 2 quadratic equations, and from there you have these different orbits due to the Pell equation solutions which sort of come out. And that is something which is very remarkable and quite interesting. Unfortunately, I didn't mention the entire framework over here, so I don't know how much more I have to motivate it to say a lot more. But we can talk a lot more about this at length after this talk too.
Yeah, I just wanted to point out that in our recent work with the Charles Cosniero and Guillaume Beaujard, buried in an appendix, we had given a formula giving the Fourier coefficients of 1/phi10 at any point in the what you call the Ziegler upper half plane, in terms of polar degeneracies, in terms of half BPS degeneracies, and the formula was really just a sum over GL2Z modulo some finite subgroup, dihedral subgroup. So I wonder whether the formulas are the same, and maybe what all the complications come by unpackaging this sum and picking out what contributions are non-zero and which ones turn out to be zero coincidentally. Right? Okay, it's just a comment.
Oh, that's quite interesting. I haven't looked at this. Maybe I'll look at it and write you an email, or we can chat a little bit more about this in the future. Yeah. But that's a good thing. Thanks for the comment.
Okay. Oh, you have a question, Bill.
So hi, this is Marty.
Hi, Marty.
So I mean, I have a question again about dyonic metamorphosis, and so I think I understood the mathematical details studying your paper. So the question would be, do you have any kind of intuition as why dyonic metamorphosis you have to make infinite identifications, why electric or magnetic it's only 2?
Oh yes, good. So the reason for that is that if you look at, so basically what is happening in metamorphosis is that you are, okay, so let me first say, so you take a charge vector NML and let this have a particular breakdown N gamma, M gamma, L gamma at a wall gamma, okay? Such that N gamma equals -1 or N gamma equals -1. So it'll be either electric or magnetic. And here I have the definition for what the dual wall actually is. So basically when you're actually doing metamorphosis, what you see is that you define this new wall gamma tilde, defined by this action over here. And once you take this and try to compute N gamma tilde, M gamma tilde, and L gamma tilde, what you actually see is that N gamma tilde, M gamma tilde are exactly the same as N gamma and M gamma. It's only that L gamma changes signs when it goes to L gamma tilde. So really what's happening here is that, and when you try to take, when you try to apply this particular thing again for gamma tilde, you recover back the gamma, right? So you apply the same equation twice, you get back gamma again. So that's the Z2 action of it.
No, okay. No, I mean, wait, I think I got this, but
so the actual coming back. So this is the mathematical thing, but there's a physical intuition. The physical intuition basically is that what actually is happening is that you have a bound state of half BPS states, right? And there is some electric and magnetic. They have an electric and magnetic center with some angular momentum that sort of keeps them together, or there's some angular momentum between them, L, okay? So basically what happens in bound state metamorphosis is telling you that there is also a different wall with a similar configuration of N and M, but with probably a different sign in L gamma, okay? And so basically when you do metamorphosis, what you're doing is that you're identifying only the electric and the magnetic center in the case of single charge metamorphosis. But the moment you go to dyonic metamorphosis, what happens is that because the structure of the sequence that I have over here, I have 2 possibilities. One is that I can start off with, let's take, I have both N gamma and M gamma equals -1. And I can say that, okay, first let me start off by identifying the electric center with a different breakdown configuration, which also has the same value of N gamma equals -1. And then once I go to this new guy over here, I can say, okay, so now let's see what happens if I apply the same thing again. But if you only identify the electric center again, basically what happens is you would come back because of Z2 action. But now, because again, the magnetic charge also equals -1 at this particular breakdown, you can start generating an infinite set in the sense that you can start first identifying the electric center, which is -1, but then you identify the magnetic center, and then you do the electric center, and then the magnetic. Or you can start off with the magnetic, then do the electric, and then the magnetic, then the electric, and so on and so forth. So you can do this repetitively and recursively. And that's why you basically get an infinite set instead of the case of the electric or magnetic metamorphosis, where there's only one possible identification. That is, you identify only one possible center. And the moment you identify twice, it's basically a Z2 close. It's closed into the action of Z2.
Mm-hmm.
Okay.
Okay.
But
okay.
That's basically
okay. Thanks.
Happening.
Thanks.
Okay. Thanks a lot. So, is there no other questions? Let's thank Abhiram again.
Excellent.
Fabulous. So thanks, Abhiram. And this is a smooth segue to the next talk by Marty Rossello, who is going to be talking from the workshop center here in Lisbon. So Marty Rossello from Romania will be talking about, let me just see whether your screen sharing works. You want to try screen sharing?
No, I don't know how to do it.
Oh, just okay.
Okay, that's the one. Okay.
You have to first put the whole thing in full screen, the presentation in full screen.
This thing? No,
the presentation first. Put it in full screen. Okay, now go to the Zoom window. You have to allow it on the definitions.
Okay, wait. Sorry about that.
Okay, go to share screen. Left here.
Okay.
Just click on it.
Okay, excellent.
So, hi.
Okay, so we're happy to have Marty Rossello giving the second talk of the session. He's going to tell us about arithmetic of decay walls through continuous fractions, an exact dynamic counting solution. Okay, great.
So thank you. This is going to be about work that appeared this summer on the archive with Gabriel Cardoso and Suresh Nampuri, which are the organizers of this workshop. So thank you for inviting me. And well, I have to say that there will be some overlap with the previous talk. But so sorry for the experts that you will hear something twice. But for the non-experts, I guess it's a good thing to hear the same thing, but differently. So let's start. Okay. So as a general comment, any theory of quantum gravity should be able to explain the black hole, the microscopic origin of the black hole entropy. String theory has attained some success at it for some restricted class of theories, in particular supersymmetric string theories. So in this talk, we will talk about the microscopic degeneracies of, so the degeneracies of microstates in n=4 supersymmetric string theory, in particular the CAGL models. And even more in particular, we'll study the degeneracies of a special class of 1/4 BPS diodes, which we call Decten diodes. So as I said before, so this project was inspired by the previous talk. So these were the results of Chowdhury, Kedambi, Murthy, Reis, and Russ. And here so this is not an extension of the results. This is a different way to look at the same problem. So in our way, we can circumvent the on-state metamorphosis phenomenon. And in this way, so this new systematic way allows us to go from the n equals 1, so the heterodox in theory, to Warby-folded models, more general cases. So in this talk, we will be talking about dyonic degeneracies. These are in the models we will consider that they are encoded in some SUGRA modular forms of genus 2. And these SUGRA modular forms are meromorphic, and this meromorphicity comes associated with the wall crossing phenomenon. So we'll see. And this wall crossing can be seen in this case as you move through the moduli space, there are some bound states that disappear from the spectrum of the theory. Therefore, the degeneracies are constant in some chambers of the moduli space, and they jump when crossing some walls. So we will use this wall crossing phenomenon to our advantage. So we'll use it in our favor to encode the dyonic degeneracies of a particular class of dyons in the continued fraction expansion of a rational number. So this will be a very explicit description of the degeneracies. So this line of thought would be the outline of the talk, and this is what I'm going to talk about now. So we will be working on CHL models, which are a special type of supersymmetry preserving orbifolds of heterotic string theory compactified on T6. We'll be only considering the orbifold number to be 1, 2, 3, 5, and 7, where 1 is an orbifolded theory, so the original heterotic string theory in T6. And this would be the previous talk. So these models have R-abelian gauge fields given by this formula, and the S-duality group is reduced through the orbifolding procedure to a congruent subgroup of the original PSL2 group. So that is, the diagonals have to be congruent to 1, and the lower left entry to 0 mod n. The T-duality group is a subgroup of some orthogonal group, some special orthogonal group. We don't need the details about it. And the U-duality group is just the product of the two groups. We want to study 1/4 BPS states in these models. And generic 1/4 BPS states carries both electric and magnetic charges, hence the name dyons. So charges with respect to the abelian gauge fields. And so these charges lie in some charge lattice, and therefore we can take, we don't need the details, and so therefore we can take their inner product to form a T-duality invariance. So this would be what we will call M, N, and L, which are the magnetic charge squared, the electric charge squared, and the electric times magnetic. So notice that M and L will be always integers, but N can be a fractional integer depending on the orbifold number. So if you're confused about this N, just think about heterotic string theory, because this, so N equals 1. And at the end, I will just mention how to extend it to N greater than 1. So the dyonic degeneracies for these charge vectors turn out to be encoded in only in terms of the T-duality invariance for the cases we will study. And we will differentiate between two types of dyons, that is single-centered or two-centered. And single-centered 1/4 BPS dyonic black holes, so single-centered 1/4 BPS states can gravitate to form black holes with finite or zero horizon area in two-derivative gravity, while two-centered bound states of 1/2 BPS constituents will not, of course. And the important thing about these bound states is that they can decay in the when moving through the modular space, and therefore they are called decadent or mortal, and therefore and hence the single-centered states are called immortal. So there are more duality invariants that we will be looking at. The first one would be the discriminant, which is a particular combination of the T-duality invariants. And this is a U-duality invariant. And there is another one, which is the torsion, which is a particular combination of so we're just looking at the GCD of particular combination of charges. But in this talk, I will only look at torsion 1, so the GCD is equals to 1. there are some more details about the case for I greater than 1 in the paper, if you are interested in it. So the important thing about the discriminant is that when it's positive and the dion is single-centered, the area of the black hole grows like the square root of the discriminant. Therefore, for it to form a black hole with a finite horizon area, we need always the discriminant to be positive. So in this talk, we will be focusing on the other case. We will look at discriminant which will be less or equal than 0. Discriminant less or equal than 0, less than 0 will always be so two center states with negative discriminant, there will always be two center states, because it's impossible to form a black hole with imaginary area, while the discriminant equals to 0 can be either two center or single center states. So as said earlier, the degeneracies are encoded in a SUGRA modular form of genus 2, meaning a particular so actually they will be encoded in SUGRA modular forms of a subgroup of the genus 2 modular group, which means that we'll take the period matrix of a genus 2 surface, which satisfies some positivity condition. When we transform this matrix in some SP2Z way, the SUGRA modular form transforms in this particular way, where K is called the weight of the SUGRA modular form. So these degeneracies are encoded in this particular way, which is we take 1 over the SUGRA and we Fourier expand, and these coefficients are the degeneracies of a dion with these theoretic invariants. An important thing about this is that M and N times capital N are always have always to be greater or equal than -1, which we will use for our purposes. And another important thing is that the group gamma 0 will be a subgroup of this G tilde group, and the SUGRA modular forms will be invariant under gamma 0. So if you want to know the weights that we'll be looking at, will be 10, 6, 4, and 2, and 1, for N being 1, 2, 3, 5, 7. So I said that these SUGRA modular forms are meromorphic. So therefore, when we are extracting the degeneracies through a contour integral, depending on the contour that we choose, if we move the contour, we could cross the pole. And this is related to, so therefore the degeneracy would jump, would change. So in this particular setting, this is understood as the disappearance or disappearance of the two center Gauss states. So that when we move through the moduli space, they can appear or disappear. So a prototypical example of wall crossing would be take a generating function to be 1 over 1 minus x. This has the typical geometric T expansion for the modulus being less than 1. Or for when the modulus is greater than 1, you have to do the trick of multiplying by x to the -1 up and down. And this is the series expansion. So this would be a prototypical wall crossing phenomenon, because inside the unit circle, this would be the Fourier coefficients 1, but outside the unit circle, and they jump and they change. Now that we know how to understand the wall crossing, we only need to know what are the poles of these signals, right? So the relevant poles that for our problem are given by this equation. No, sorry, this blue equation, where these coefficients P, Q, R, S are integers that belong to this subgroup. Sorry, now I give the definition of this subgroup. So this is a bigger subgroup than the S duality group, and it's only defined by R being 0 mod N. So we can project these three variables to the upper half plane by this particular combination, and we can represent the walls. We can represent the poles in here into walls in this upper half plane or the Poincare disk where things are more symmetric. So these walls are given by lines which join the rational numbers P over R, so first column, and Q over S, second column. So this is the n equals 1 case, this is the drawing. When R or S are 0, they become straight lines that go from integers to I infinity. And for the n equals 1 case, these lines here are called the typical Faraday lines. Now the next ingredient that we need to, so the next thing we think to understand is the.
Sorry, Marty, I have a question.
Yes.
So the previous slide, you had this 1 over 5k.
Mm-hmm.
I think there's an argument that I've sort of forgotten or something. In the old paper by Ashok, Jatkar, and Justin David, they construct these two different sorts of Siegel forms, 1 over phi and 1 over phi tilde. What is the justification for using one over the other? I've forgotten. Could you remind me, please?
Yeah. So, I mean, sorry, I skipped this, but we are using the phi tilde. So this is the phi tilde in the
phi tilde over here.
Yeah, this is the phi tilde, the one which encodes the degeneracies. Okay. So yeah, you're right. Sorry, I should have mentioned this. So in the paper by Jatkar, they build a phi function, then they perform a Siegel transformation, which transforms it into the phi tilde, and this is the one which really encodes the degeneracies. So yeah, sorry, we are using phi tilde. So okay, now we have to understand the decay modes. Given a wall of marginal stability determined by this matrix in gamma 0n, dion with charges Q and P decays in the following way, so that you can see that these two dions have parallel charges. So these are two 1/2 BPS states. And we'll look at the particular decay, which is the one corresponding to elementary identity matrix. We call it the elementary split because it goes from QP, so this matrix can be seen as a decay going to purely electric and purely magnetic charges. And this is the V equals 0 pole. Now we first want to understand this elementary split. So this is the decay, and want to know how the degeneracy changes when crossing this pole. So we can understand this by looking at the V going to 0 limit of the Siegels, which is given by this expression, where these are the magnetic and electric 1/2 BPS counting functions. We will express the Fourier expansions like this. There are some particular modular forms. In the case of n equals to 1, this is the eta 2 24, 1 over eta 2 24. So we can see that, computing the residue at this pole, we can get that the change in the degeneracy when crossing from one side to the other is given by this expression. This would be the residue at this point for a given charge aliens M and L. So now we want to extend this to any split. We can do this by mapping any matrix to the identity matrix, and then computing the split there. So this would be in words. These are the formulas. This would be the formula for ascending words. Then we should compute the transformed charge linears, which is the M gamma and gamma L gamma of the previous talk. And therefore the change in the degeneracy is given by the previous formula, but using the transformed charge linears. So this is what it said. So this is the wall crossing formula we will be using in this talk. So to summarize, the wall crossing jump contribution of a dion with charges QP, because the generic line of marginal stability given by a matrix in gamma 0n, to the ionic degeneracy formula is equal to the jump contribution of the dion with the transformed charges across the elementary T wall, the identity, basically. And this is the formula. Fine. So now we have all the ingredients to pose our dion counting problem. So as said, we are interested in dions with discriminant less or equal than 0 and we further will also impose this bound for practical purposes. So with this bound we can get the whole degeneracies. Now we want to compute the degeneracies of these Chapman linears, and we have to specify a chamber in the normalized space in the upper half plane. And we, following Sen and Kidambi et al., we choose the R chamber. So the R chamber is given by the chamber which touches the walls between 0 and I infinity, and 1 and I infinity. And here note that I draw this with dotted, because these walls could be there or not, depending on the orbital number. So now, circumventing the BMS phenomenon, instead of looking at all the possible decays of a given dion, we just want to find a decay path in the upper half plane, such that we start in the R chamber, we move through the upper half plane until we end up in some chamber in which we can compute the degeneracy easily. So we will call the sequence of decays that we will find the set by the set WMNL, following the previous notation, and the final point as a star. So then the dyonic degeneracy is given by this formula: the endpoint degeneracy plus all the wall crossing contributions. More explicitly, endpoint degeneracy plus all the wall crossing contributions for the walls that we have crossed. So here I should say that this set WMNL, even though we have used the same notation, is not exactly the same as the set given in the previous talk. So for us, the set is a sequence, so it's an ordered set of walls, and which encodes the walls that we have crossed from going to the R chamber to some chamber. And it's possible that it doesn't encode the whole degeneracy, because we are allowing for this to be non-zero. In the case in this is 0, the set WMNL is the same as in the previous talk. So our hope is that we can compute this. So if possible, to be 0, or to be easily computed. So how are we going to do this? Well, first we'll focus on n equals to 1.
Sorry, question? Martin?
Yes. Yes.
This is Samir. I'm a little confused about this D star in the previous talk, previous slide. So isn't it true that any negative discriminant state will always decay?
Yes. But I mean,
if it will always decay, then shouldn't D star be 0?
So I mean, two things. I mean, it is true, but we are also allowing for 0 discriminant states.
Oh, I see. It's that. Okay, then it's fine.
And then the chamber in which this is 0, maybe it's not so easy to find. Yeah. So we are allowing for this.
I see. So that's a practical issue, though, right?
Yeah, exactly.
Okay, good. Thanks.
So we will be restricting ourselves to n equals 1 and negative discriminant. So 1, we should be able to find the chamber in which the endpoint degeneracy is 0. That's right. So there can be some, so we can give some arguments of why to go downwards. We choose to go downwards. Notice that we could go to any other chamber in the knowledge space, but we choose to go downwards, and there are some stability arguments to be given, or also we could use the arguments in the previous talk as these are the negative discriminant states here that we are considering are part of the finite modular form. So therefore, these walls will not contribute. Fine. So, I mean, I don't need to give the motivation because it will work. So we choose to go downwards, and the first thing to realize is that going downwards consists in a left-right choice given by these two matrices. So the first wall that we will encounter will always be this matrix, the U matrix, and then we have a choice. We have two choices: a left or right, then left or right, left or right. So this can be seen as given by right multiplication by U or T. So this is the first thing to realize, and this is what defines our arithmetic of decay walls. So specifying a path, a downward path, is the same as giving a particular combination of U and T matrices. Therefore, we can decompose any matrix in the matrix in this path as a particular combination of U and T matrices, which will always start like this. And therefore, our set is given by this particular combination of U and T matrices, finishing at the gamma star wall, which is the wall which is just above our finite point. Fine. So the last thing to notice here is that if I give you a gamma star a wall, be it like this one, it completely determines the walls that are above it. So given gamma star, we know the whole set WMNL. So we only need to determine where is gamma star, what will be our choice. So for our previous constraints, we know by an argument by Sen, or I mean, it's a real simple argument, that there is a gamma star such that M gamma star or N gamma star will be less than -1. So this is what Samir said right now, which implies that the degeneracy will be 0, because there are no degeneracies with this satisfying this. So instead of considering this condition, we consider a weaker condition, which is like take M gamma star to be less than 0. Fine. We could also take N gamma star to be less than 0, but this is a choice. I mean, that we could exchange them and nothing would change. So this condition is actually this condition, and it can be translated in these two inequalities, which these are the roots of the associated polynomial here.
Sorry, Matti, I have a quick question. So did you already mention as to why once you go, sorry, I had to like tune out a little bit, but do you mention why gamma star is the endpoint? Why is there like a mathematical reason why below any of these gamma star walls, there should be no contribution to M gamma greater than -1 or N gamma greater than -1?
So there exists a M gamma star for this to happen. This is an argument given by Sen. You're asking if it's downwards, you mean?
Yeah.
It's below. So I mean, I'm sure this is true. Yeah. So
I'm sure it's true too, but like I just this is something you and I had a long time ago. But why is it true? That's the question. How one is sure that once you go below gamma star that there should be no contribution at all? Why does it terminate at gamma star?
So I mean, if gamma star satisfies this, then that's fine. The thing is, fine. So then, if you look at these conditions, P over R has to be between these two numbers, right?
Yeah.
So this is basically more or less 1/2. So it is between 0 and 1. This is between 0 and 1 always. No, 1/2 actually, right?
Yeah.
And so on these numbers, so there will always be a decay between 0 and 1/2. That's actually, so this condition will always be satisfied between 0 and 1/2.
Okay.
Once you get to a negative M, you can also get to a even more negative M. So and therefore, you know that it will be below that wall.
Okay.
This would be the argument, I think. But okay. So if it's not clear, I think it will be clearer later. So we have to impose another set of conditions, which these ones are more technical. It's worth explaining by Hardy-Ram. And these ones, so we can restrict ourselves to the lower entries to be positive and L gamma star to be positive. So this is related to the fact that we want to compute decays of 1/2 BPS, so bound states which exist in the R chamber, and when going down they decay. So to be sure that this is the case and not the other case, so that when you go down, bound state appears. These are actually the technical conditions. I mean, these are not the only ones, but these are enough. And so fine. So for these conditions to be satisfied, it's enough to satisfy these two inequalities. This is just a matter of computation. So from our constraints, we have arrived to these two conditions to be satisfied. And looking at this, one can see that they are solved by this choice. I mean, this is not the only choice, of course. There are, I don't know, infinitely many choices probably, but this is the simplest one. If you look at the first one, L divided by 2m here will be always satisfied. And if you choose P and R to be L divided by 2m, this becomes the same equation as this one. So this means that these form a PSL2Z matrix, so that it becomes an inequality. So I hope everyone is convinced that this is true. And here, of course, since this is a PSL2Z matrix, you have to divide by the GCD of the two numbers. So now from our conditions, we have arrived to a gamma star with the first column specified by this. This has an associated transformed charges by this. They have this form, and since the discriminant is always negative, is our condition m gamma star less than 0 is true, and our condition L gamma star greater than 0 is true. So what we've done is consistent. And there's only one thing left now, which is to find the second column, Q and S. So there are again infinitely many possibilities, but so we want to find a systematic way to specify this column. So it turns out that taking the continued fraction of this number, the continued fraction expansion, completely determines the second column, as we will see. So how does the continued fraction appear? I hope that everyone has seen this in their lives, but I'm probably forgotten. But when you compute Euclid's algorithm to find the GCD, which would be this number, is the number you're looking for, there appear a set of numbers here, the AIs, and this from the continued fraction expansion of L divided by 2m. So one can also compute the continued fraction directly, which is find this expansion. And so these numbers are encoded in the continued fraction of L divided by 2m. So since L divided by 2m is between 0 and 1, this number will always be 0. And so this is a classical result of continued fractions, that you can multiply the matrices T and U in this particular way, such that the whole product of matrices, so these are U and T matrices interchangeably as before, the whole product of matrices will be a PSL2Z matrix with a column, depending on the oddness or evenness or n. So sorry, this n is this n, not the previous m and l. So such that so one of the columns will be L divided by the GCD 2m divided by the GCD, and the other one is completely specified by the continued fraction of L divided by 2m. So L divided by 2m gives us all the information that we need. And notice that this matrix, it's even built in the explicit form that we were looking for. So this completely determines the sequence W, M, and L. So with this, we could say that we have solved our problem, which was to explicitly determine the set W, M, and L. So that is, given charges M and L with negative discriminant and satisfying this bound, you only have to compute the continued fraction of this number. This completely defines your set W, M, and L. And then our formula becomes this, where earlier we didn't know what was this, and now we know that this is a particular set built out of this. So the only thing left is to compute this number. So this is the punchline of the talk, I guess. So the set WMNL, our set WMNL, is completely determined by the ratio of these two numbers, L and 2M. So to see what's going on, because I guess that the first time you see this can be confusing. Take an example. Take L divided by 2m to be 2/7. This has a simple continued fraction, which is 0, 3, 2. And we can compute the gamma star matrix, the product of 1, 0, 3, 1, 1, 2, 0, 1. And of course, we get 2/7 and 1/3. So this is the QS that we were looking earlier. So we can draw this in the upper half plane as starting from the air chamber. We cross these 3 walls given by the 3 U matrices, then multiply by 2 extra T walls. So this is our path. We start from the air chamber and we go to the chamber below the wall given by this matrix. And the walls are actually, of course, given by the 3U to the 3 powers of U and extra T multiplication. So yeah, I think I have time. So actually, we don't even have to multiply this. If you have ever worked with continued fractions, you will know that the columns of the next matrix are the sum of the previous columns. So this is like how children sum the fractions. So this is called the median sum. So, and from this we can extract this sentence. So from going to the air chamber to the wall below the matrix that has this column, the column with ln to m, one crosses the sum of the continued fraction coefficients walls. So this will be the number of walls that we cross. Fine. So as said earlier, there is one thing left to determine, which is the endpoint degeneracy. Recall that this was our transform charge in the gamma star, so in the star endpoint, which is given by this, and this was this is always negative. So we have 2 options. Either this is less than -1, therefore the degeneracy is 0, then the problem is solved. Everything is encoded in the continued fractional L divided by 2m, and that's it. There's the second possibility, which is that m gamma star will be -1. So in this case, the degeneracy will in general not be 0, but it can be computed very simply. So how? Well, the transform charges will have this form. So again, this can be done interchangeably for n gamma star. So the transform changes would be these ones, and we can apply extra t transformations, and this is how it transforms. So for t to the j, this would be the transform charges. So the m isn't changed, n becomes this, and since L star was positive, this can be made arbitrarily negative. In concretely, it can be made less than -1. Therefore, we can go from this chamber, the star chamber, to a chamber in which the degeneracy will be 0. And L gamma star will always be, so the transform L will keep being positive. So this is what we're looking for. Therefore, the degeneracy in T star is, once you know the N star and L star numbers, so the transform charges in the chamber, the degeneracy D star is given by this formula. So if we had done this for N gamma star instead, it would be U to the J transformations. One can say that this is actually equivalent to extending the continued fraction of L divided by 2m to this continued fraction. So this actually, this already incorporates the choice of U and T. So this is done. So if you know J0, that would be the whole answer. I think that's all I wanted to say here. So our problem for n equals to 1 and negative discriminant is always 0. So okay, and maybe I could say something if I have time. Yes. So this case can actually link to one of the Jacobi forms of the Igusa-Cast form, the one which has negative index. So doing this is actually computing the Fourier coefficients of the Jacobi form, but I don't want to go into these details. Or I mean, this has been computed, and so this reasoning and the Fourier coefficients given by the formulas completely coincide. So now we turn to the 0 discriminant case, and we keep n being 1. So now a priori we don't have a chamber in which the degeneracy will be 0, but let's say that we keep the same reasoning. So we compute the continued fraction of L divided by 2m. We compute the transform charges. But now notice that since the discriminant is 0, m gamma star and L gamma star will be 0 directly. And the next thing to notice is that the PSL2Z action on the charge bilinears preserves the GCD of the 3 charge bilinears. This is easy to see, I mean, okay. And therefore, the other charge bilinear that we are looking at has to be the GCD. So there is a new discrete invariant entering the game of the counting. So this guy is now entering the game. So we have built a sequence of decay walls by the continuous function well divided by 2n, such that the last charge bilinear is so the last charge bilinears are either 0 G tilde 0 or G tilde 0 0. So the only thing left now is what is this degeneracy? Well, to find it, we will need to expand the inverse of the Ikusakas form. So maybe I should pause here. What is this? So this is the Fourier-Jacobi expansion of Siegel modular forms. This is Siegel modular form, and these are Jacobi forms. M would be the index of the Jacobi form, and all of them have the same weight as this guy. So this is the psi -1 mentioned earlier, but we want to look at the greater or equal than 0 index. So these Jacobi forms, as explained in this great paper or book, or I don't know. So the amazing results of this work were that you can split the Jacobi form psi m in 2 parts: the finite and the polar part, where the polar encodes the wall crossing through the vertical walls in the upper half plane. So we want to focus on the finite part for m equals to 0, because as earlier we want to compute m equals to 0 states, and they are immortal, so they have to be here. So you can actually expand this. This is given by the Weierstrass. The whole thing would be given by the Weierstrass divided by eta to the 24. And it turns out that the finite part is given by the Eisenstein 2 divided by eta to the 24. So this can be seen as minus the derivative of the 1 over eta to the 24. So its Fourier expansion is really simple, and it's given by this. So this will be the degeneracy that we're looking for. Therefore, our final formula for delta equals 0 and n equals to 1 is given by this one. So we compute, again, the continuous fraction value divided by 2m, and we compute, and this would be the degeneracy of the endpoint. So notice that there is a minus sign here, and not anymore here, because there is a -1 to the L plus 1. But for a negative discriminant, we always need L to be even. So the signs cancel, and this is the final formula. So in particular, as a byproduct, we have gotten this very nice formula, which is that if I give you a set of charge bilinears, M and an L, with 0 discriminant, the immortal contribution of these charge bilinears is given by this simple formula. You only have to compute their GCD.
Can you say again, what's G tilde?
G tilde is the GCD of L divided by 2 of the 3 numbers. Sorry, yes. So yes, compute the GCD of these 3 numbers, and this is the formula. Fine. So now the last thing to look at, this would be the extension to n greater than 1. So I don't want to go into details because things are more intricate, but I want to say that the logic is exactly the same. So the first thing to notice, so what changes when we go from n equals to 1 to n greater than 1, is that the walls that exist below the R chamber are different. So there are less walls for each n. So this in particular has some implication. So as for instance, it could be that the first wall that you will cross for the n equals to 1 is always this one. But for n equals to 5, for instance, would be this one. And it could be that the contribution that it gives is already 0, this wall. So this tells you that if you're looking at the degeneracies of M and L satisfying the previous bounds, it's very probable that you will find zeros. And indeed, when you Fourier expand with a computer, you find lots of zeros. So everything is consistent. So what we do here, we proceed as earlier, we compute the continuous fraction of L divided by 2m. But now, so as if it was for the n equals to 1 case, but now the matrices that appear in our set, we select the ones which are in gamma 0m. So there is a detail that I'm hiding here, which is that there is another thing that the n equals to 1 case has and greater than 1 doesn't have, which is that any wall has two matrices representing it. That is a matrix or a matrix interchanging the columns and multiplying by -1. They represent the same wall. So, and therefore we had the previous conditions. The lower end is being positive, but now this is not the case anymore. So the details are a bit more involved, but we can do exactly the same procedure. So if you want to see the details, just in the paper, I think it's very explicit. So the last thing that we have to look at would be the zero discriminant case for n greater than 1. So we should expand the seagulls and look for the finite part with the 0 index. So luckily, it was computed 2 years ago by Bossart, Kosniogho, and Piolin. So as you see, this is a generalization of the previous formula. So we didn't even have to look for this. These were given to us. And we checked our procedures with all this information and everything checked out exactly. So I think...
Hey, Marty, I have a question.
Yes.
So it's of a two-parter. So first one is that what happens if you also add your Atkin linear involution into gamma naught n and take it gamma naught n plus? Then that will give you a way to sort of go between these different walls, right?
So sorry, can you say the Atkin linear involution?
Atkin linear involution. So that basically is adding the extra. I mean, the reason you can't go between different walls is that there's no sort of S transformation for gamma naught n. But you can add this extra involution where tau goes to -1/n tau, and then you can sort of compound gamma naught n to something called gamma naught n plus. And why would one not consider that gamma naught n plus instead of gamma naught n here?
So we didn't need it, I think, but so I don't know the details of this case. I'm sorry. Maybe it's even better. It's more explicit with what you've said, but
because if you don't have this thing, then how would your end result be explicitly S-dual invariant? I mean, under S transforms, or the equivalent of S transforms.
No, it's not. So that's the point. We go down, we cross some walls, and then we look at these walls and the S transformed walls. And of the whole set of walls, we pick up the ones which are in. So it's like doubling the set of walls that you're looking at. And then from the two sets, you select the ones which are in gamma 0n. So now you're allowing for negative values in the lower entries. And therefore you have to take only the L less than 0 walls. But we know that they will have less than 0 walls. So I think that, so thank you, because I skipped the thing, which is, let me go back. Sorry for that. So when I gave these two conditions, when you pick the column to be like this, so this condition is the condition for the convergence of a continuous fraction. So this is the condition related to the R, S, and L gamma star greater than 0. So we know that not only gamma star will satisfy this, all the walls that will cross will satisfy this. So we are not worried about the positive or negative values of L. I don't know if this helped.
Yeah, I mean, like
I think the future evolution with the exchange phi k and phi twiddle k. So if you're interested in only extracting the contributions from one, you cannot use this.
Yeah, that's right. So you would have to take the phi k as well.
Okay, so I mean, it could be, yeah, it could simplify some things, but then make more difficult a lot of things. So I don't know. I will look into it.
Yeah. Also, like another thing would be that your Rademacher expansion would require some cusp identification that would still, maybe I'm wrong, maybe Val knows this a bit better than I do, but there'd be some necessary cusp identification. So the articulated evolution would go a long way into also fitting in with the theme of the previous talk. Yeah, but anyway, I don't want to.
No. So we didn't go into Rademacher for n greater than 1. We just said if there exists, then it will encode this. What we have done will encode the immortal degeneracies, but we didn't go into it.
Okay.
So this is an open question, I think. But okay. Thank you for that. I will look into it. So I think I still have some time. So before summarizing, maybe I could give some example. So, okay, let's look at the cherry-picked example. So I chose this example such that the pictures are the same as earlier, so I don't have to change anything. With n equals to 1, the simplest case, and such the discriminant is 0. So the example is M and L, given by these values 49, 4, and 28. So the walls we computed earlier. Now we have to compute the GCD of these three numbers because this is a zero discriminant state. The GCD is 1. So it's 2 times 3 and 24. Okay, this is this number. We have to compute the transformed charges associated to each wall. And we have to, and the answer is the immortal degeneracy minus the degeneracy from wall crossing. And this is the number that we get. So I mean, so this is to highlight that doing even childish computations, if you know these coefficients, you can get this huge number, and then you go to your computer, you ask it to compute the Fourier expansion until m equals 50. So then you wait for several hours and you get exactly the same result. So I mean, I don't think we need to a numerical verification of what we do, because I think that the reasoning is clean enough, especially for n equals to 1. But it's nice to see that everything works out. So summarizing, we have used continued fractions to set up an arithmetic of the K walls, which we use to explicitly compute all the polar coefficients of 1 over phi K, and the polar and also the zero discriminant states. And let me close with a comment. So when doing this, we read a lot of stuff, and maybe one could want a bigger motivation, stronger motivation for the appearance of continued fractions. So one could say that they only appear because we are working with SL2Z. But I think that there is a stronger motivation, which would be that the moment in which you identify your T-derived invariants, M and L, as the coefficients of a binary quadratic form. So if you look at negative discriminant states, this means that the form is indefinite. And so there is a very classical result 2 centuries ago, I think, by Gauss, that so which there is an algorithm by Gauss called the Gauss reduction algorithm to compute some equivalence classes of indefinite quadratic forms. So this algorithm is exactly equivalent as computing the continued fraction of an irrational number. It is also a well-established result, and I think this gives more naturalness to the appearance of the continued fractions in our computations. So instead of computing the continued fraction of some irrational number, which would be the roots of this form, we compute the continued fraction of L divided by 2m, which would be the midpoint of the two roots, and this gives us the best path to go down in the upper half plane. So these identifications are consistent with the work by Moore called the arithmetic attractor, in which he related the growth of the, I won't go into this, but the growth of the entropy associated to the discriminant as the number of equivalence classes of positive definite quadratic forms. But But I just want to say that this is a nice point of view, and that there is now a recent interest in these topics, and that I think it's worth exploring. So that's it.
Okay, let's thank Marty. Questions, comments?
Can I go? Can I have a few questions?
Mm-hmm.
Okay. So
Sorry, while you're asking the question, can you just go one slide back so that I can study the example?
The example?
Yeah, thanks. Yeah.
Yeah, sorry, these are a lot of numbers.
Samir, are you asking the question or are you just studying the example?
No, please go on.
Okay.
I'm not hearing anything. Abiram?
Sorry, I'm on mute.
Okay.
Yeah, the case where you mentioned that you try to restrict to m equals 0, and then you do this d of 0, g tilde 0.
Mm-hmm.
Yeah. And you want, so this is where I have a slight confusion here. So from the supergravity side, the localization, I think if I'm not entirely mistaken, is that the localization restricts to m greater than n. And then through a series of calculations, one can show that in that case, the attractor region then sits between 0 and 1. That's the region R that we have over here. But then if you restrict to m equals 0, in order for your contour to still sit in such a way that R is the necessary chamber, then you're already restricting yourself to n equals 1. So g tilde equals -1 already. Do you have a comment on that? Or because m has to be greater than n.
So yeah, but this, I mean, this is in supergravity we're looking at. So the fact that is,
I get that. I get that.
Yeah.
But the same m and n L hold even in supergravity. It's just a different side of the coin. But if you, the point is that if you want to use R, I think it means that you have to take m greater than n in your charge.
I mean, you could look at instead of z of 0, g tilde 0. So this is the same number as g tilde 0, 0. So they have the same degeneracy. So you could look at this case. I don't know.
Yeah, but then I thought you broke the electric magnetic duality because you don't have gamma naught n plus.
Yeah, but once you are looking at the immortal guys, I think you don't care about the volts. So this degeneracy is the same in the whole plane. So the immortal part, I mean.
And just one comment on, like, when you said this agrees with Moore's 98 paper, are you talking about the arithmetic and attractor stuff, or?
Mm-hmm. Yeah, no, just like that. So yeah. In Moore's,
but there the quadratic forms come from attractor varieties, not necessarily the walls and margin stabilities that we have here.
No, I mean, I completely agree. It's just that the identification. So first he works with positive discriminant. Where you say that if you look at negative discriminant also as binary quadratic forms, so that there are some, I think that there's some extra insight that you can get. This is the only thing that
Yeah, but I just want to give a quick comment on, like, the stuff that you mentioned. You can also do this Gauss decomposition for, you can also use this higher decomposition. So not just the Gauss decomposition from 100 years ago, whatever, but there's also more recent work by Manjul Bhargava on higher decomposition laws. And then you can also study cubic forms, quartic forms, and all these kinds of things. And they also have some interesting relations to sort of state counts or point counts in moduli spaces or BPS counts. And there's actually a paper by Murat Günaydın, Shamit Kachru, and Arnav Tripathi on this Bhargava's invariant theory. So I think that's also, if you're mentioning that, that's also the thing, like something that you should probably look into. That's a very interesting paper. Yeah.
So sorry, yeah, by Kachru, I only mentioned one paper, but yeah, I'm aware that there are 3 or 4 papers about this topic, yes. Yeah, I mean, I haven't looked into it, to be honest, but I think it's very interesting.
Well, there, just comment, like categorically, like there in those papers, it's not really walls or margin stability they're looking to count, but probably different sort of point counts in moduli space. So although you're right that there are these binary quadratic forms, the nature or the origin of these quadratic forms or cubic forms or whatever is slightly different. But yes, it's a very interesting subject.
Yeah, no. You're right. You're right. Yes, of course. The point is, since in this paper we're looking at negative discriminant states, these attractor varieties, I don't think you can work with them. I don't know. I'm not sure about this. But everything that I've seen with this is always positive discriminant, which is where things make sense, I would say. But yeah, so thank you for the comments. I will think about it.
Okay. Any other questions?
Yes. I have one question and a bunch of small comments. So firstly, it's very nice. I really liked the talk and the results. I hadn't read the paper, so it's really
okay.
great.
Good.
So one practical question was that this gamma star, just in the simplest case, say take n equal 1 and delta less than 0 or something like that. So is there a so we know that there is an existence of gamma star such that this sequence terminates. But can we do better than that? Is there some way to sort of say what it is a priori or something like this?
I don't know. I mean, from all the cases that I've looked, it kind of looks a bit random. So I mean, we have this description, which is very explicit, but we have lots of walls, and most of them won't contribute at the end for the negative discriminants.
Right.
So maybe there is a better choice of continued fraction. Could be, will be.
Okay.
More exact, let's say.
All right. So yeah, then I have a bunch of comments. So one comment is that so after our paper, I was trying to sort of get a different understanding of a formula and so on, and I sort of roughly went down this route, although I didn't quite put my finger on continued fraction, so it's very nice. And I had one conversation with Don Zagier once, and he pointed to a certain construction which might be useful. So I just want to put it out because many people are, a lot of people here are interested in it, and this might be useful. It's a paper of Zagier and Popa, P-O-P-A. I can send the reference in the chat, in which basically they tile the. It's something very simple. It's not very sophisticated, but they tile the upper half plane. So they have a nice way of constructing this set of matrices which tile the upper half plane. And there's one sort of subset which is very interesting, and that's the thing I think we need in this problem. So it might be sort of let's chat about this later, but it might be a reference which is useful to other people here. So that's one comment.
Thanks a lot. Thanks a lot for that.
The other comment was that so as I'm sure you know, this Brahmagupta-Pell equation is closely related to continued fractions. If you have a square minus dx square equals -1, the continued fraction of square root of d is what. Sorry, I mean the continued fraction of a over b is the convergent of square root of b. There's some statement like that which I think is well known, right? So it might be that these two approaches are actually sort of related in that way. That will be interesting to work out. So we should certainly, certainly have a discussion.
So we have a comment on that on the paper. Just one sentence because we didn't want to go into trouble. But I think that if you look at binary quadratic forms, there is the thing of the automorphs. So in the case of the dyonic metamorphosis, what you're doing is identifying automorphs. And so the equation for finding automorphs, I think it's the Brahmagupta-Pell, not the generalized one, the simplest one.
Yeah.
So we just mentioned that.
I see. Yeah.
But so yes, but I don't know.
Yeah, no, that's true. What I'm saying is that might have a direct relation with your approach with continued fraction.
Okay, I see.
Right, because there is an intrinsic relation between those two things.
No, you're right. Sorry, you're right.
Now, I had one more comment. Yeah, generally speaking, I think it's worth sort of trying to abstract the math. It may be worth trying to abstract the mathematics involved in all these things, that we're giving explicit formulas for coefficients of Jacobi forms and so on, the completely explicit formulas. I mean, there was some very old work of Skorupa, and I think the title is just by himself, and the title might be something like explicit formulas for coefficients of Jacobi forms. It's not what is needed for us, but maybe if we try to sort of abstract these results, we can present it like some kind of a generalization of that to class of mock Jacobi forms. I don't know. So that's another problem which I think from the purely mathematical side might be worth thinking about. So I can also pull out the reference for that. Otherwise, look up Skorupa and explicit or something.
Okay, thank you. I will. Okay. So I think I will have to rewatch the YouTube video. But...
No, or we can just discuss. Okay. Call me later. We can discuss it. Yeah.
Okay. Thank you very much. And so yeah. So when doing this, I thought, I mean, we are computing actually so negative discriminant coefficients of single modular forms. I mean, I'm sure that the mathematician knows all this, but I haven't found anything. So maybe this paper is the one I missed. I don't know.
I just have one more question. So in these walls of modern stability, the fractions that you get, these are all the Ferry fractions between 0 and 100, some particular thing, right? And and there's actually this very intricate relation between these Ferry fractions and this Euler-Totien function. I think I don't really know the exact thing, but you can actually work it out. I remember I did it when I started working in this problem. There are these Euler-Totien functions, and all these Ferry circles are basically just like semicircles between these various Euler-Totien functions in such a way that they don't cross or whatever. I just know that's like when you do your CHL model, was there like a generating function for the fractions that you could pull out, or is it something that you really have to work out by doing Mathematica or something?
Yeah, no, we used Mathematica. I mean, it has a function which gives you the continuous fraction, so we then think about it.
Okay.
But yeah, I think, okay.
It's just a generic question that I've had for a long time, if there is such a generating function of these fractions, even for CHL models. But yeah, I mean, Ashok seems to know about this, but he doesn't write it down explicitly in the paper on, I think, on negative discriminant states or walls of model stability n equals 4. So I could at best only do it algorithmically, but I never could write down an explicit formula for it. So I'm just asking if anyone knows this. It'd be very interesting.
I wish, you know.
Okay, any other questions? If not, let's thank Marty again. Excellent. That's it for the morning session. So we'll reconvene at 2 p.m. Lisbon time. Thanks a lot.